Hey everyone, this video is about how to train your own version of ChatGPT-like model. Now, if you ever looked how AI models are trained, you've probably come away thinking that the whole process is impossibly complex. My goal is to change that. I'd like you to think about this video as a story. At the beginning, training a large language model seems impossibly complex. At the end, I hope you feel surprised how simple the core ideas actually are. OpenAI ChatGPT is a large language model, or LLM. In just a few years, large language models have gone from research projects to tools used by hundreds of millions of people every day. They can write code, answer questions, summarize information, generate images, and increasingly behave like general purpose reasoning systems. But despite how widely these models are used, the actual training process behind them is often surprisingly difficult to understand. Most explanations quickly become buried under heavy mathematics, complex notation, and research terminology. And while the math is important, I think it sometimes hides the bigger picture, the core ideas behind how these systems actually learn. So, in this video, I want to take a different approach. My name is Sasha Lepchuk, and my goal is to explain how transform-based language models are trained using intuition first, with visual reasoning, simple examples, and only the minimum amount of math necessary to build an accurate understanding. We'll look at the full training pipeline, step by step. To keep things understandable, we'll study a simplified transformer with small matrices and a single attention block. Real LLMs stack many such blocks together. At a high level, training an LLM is fundamentally the process of adjusting large matrices so that the model becomes slightly better at predicting the next token. Remarkably, these models begin life as purely random numerical systems. At the start of training, the weights inside the network contain no language understanding, no reasoning ability, and no knowledge of the world. Through exposure to enormous text datasets and billions of small optimization updates, random matrices are transformed into systems capable of producing coherent language and remarkably sophisticated behavior. By the end of this video, you should have a clear mental model of how that transformation happens. So, let's start with the fundamental question. How does a transformer actually learn? When we talk about AI, any AI, we should first clarify one thing. Are we talking about training a model or using an already trained model, what we call inference? Today, we'll focus only on the training process. So, our goal is to create and save to file 8 two-dimensional matrices, where the number of rows and columns ranges from 128 to 10,000. Not that many. I'm sure you work with Excel tables much bigger than that. And once we are created, we'll save those 8 matrices into a file, and that file will become our AI model, ready to answer questions. You can think of it like an Excel document with 8 sheets where each cell contains a number between 0 and 1. So these are the matrices we'll be tweaking before saving them to a file. At the start, we just fill them with random numbers. Then, a little by little, we adjust those numbers to see if each change makes the model a bit smarter or a bit worse. Let's put them into context and walk through the full transformer pipeline. Hi again. To give you a quick preview of what's ahead, the entire process will feel like cooking a soup, where some ingredients are fixed, 1 kilogram of meat for example. This will be our text corpus, and some can be adjusted later, salt and pepper in case of soup or our learnable matrices in our case. When the soup is ready, we taste it, we calculate the value of our loss. And based on the calculation, we decide if soup needs adjusting, if it needs more salt or pepper. If it does, we tweak our matrices. We repeat this process until the flavor of the soup, the loss value, is satisfactory. Let's put them into context and walk through the full transformer pipeline. We start with text, lots of it, and the more, the better. We use a pre-trained model to convert text to tokens. Then we use token IDs to create token ID to embedding mappings. We'll use token IDs instead of actual words for speed. We'll also have token IDs to embedding static semantic mappings stored somewhere in memory for the same reason, for speed. Now let's look at the WTE matrix. This matrix contains the subset of data we are currently training our model on. We process text in fixed size chunks. In our example, we have loaded 512 token embeddings into the WTE matrix, and that number will define the model's maximum context length. Now we apply linear algebra and other calculations to the 128 numbered embedding vectors. And from this point on, all we'll do is to apply math to the values in the WTE matrix. About the 128 number semantic embedding vectors. The idea of semantic embedding vectors has been around for over 50 years. We live in a four-dimensional world, x, y, z, and time, t. Knowing these four values tells us exactly where we are in the universe. If we know someone else's x, y, z, and t, we can tell how far apart we are from that person. The same idea can be applied to words. The difference is that the units aren't meters or seconds. We just call them units. And instead of 4 dimensions, we have 128. So, if two words often appear close to each other in large text datasets, the distance between them in this 128 dimensional space will be small. If they rarely appear together, the distance will be large. That's what these 128 dimensional embeddings are. A position of each token in the high dimensional space. Positional encodings. We inject information about the position of each token within the 512 token window. Believe it or not, we do this by adding it to the embedding vector of the token itself. So, before this operation, the WTE matrix effectively contains information about what the word means for each token. After this operation, it contains information what this word means at this position within the 512 token context. The value that we add to each dimension of each token is a function of the token's position and the dimension's position, passed through the sign of x function for odd dimensions and the cosine of x function for even dimensions. As a result, the model can now understand word order inside of the 512 token context window. By now, our first matrix, WT, has been populated. It has a shape of 512 times 128. Let's start to mix in our learnable matrices, which will become our AI model. The big idea is to mix in values from learnable matrices into the WTE matrix. In most cases, mixing means multiplication. So, we multiply the WTE matrix by WQ, which produces the WTQ matrix, consisting of 512 new 128 dimensional vectors. We then obtain the WTK and WTV matrices in a similar way. Now, I'm going to explain why this 2017 Google publication called "Attention is All You Need" has changed everything and made smart models like ChatGPT possible. The publication suggested, instead of processing sequentially, let every word directly look at every other word. That enabled parallel processing, better long-range understanding, massively scalable training, which ultimately led to modern LLMs like OpenAI ChatGPT models. Google's idea was to train three shared matrices that convert each token into query, key, and value vectors. The query controls what this token is looking for in other tokens. The key controls how this token can be found by other tokens. And the value is the information which will be passed forward if the attention mechanism decides this token is a good match for the current query. First, we multiply query and key vectors and compute the dot product, because dot product measures similarity between what a token is searching for and what another token represents. We get a coefficient for each token pair. Then we multiply this coefficient by the token's value vector. If it's a good match, then the coefficient will be large and the value will strongly contribute to the output. If it's not a good match, then the coefficient will be tiny, almost zero, effectively suppressing that value. Mathematically, we multiply WTQ by the transpose of WTK, then divide the result by the square root of 128, so the numbers do not become too large. We then mask future tokens so that a token at position A has no information about tokens at position A plus 1, A plus 2, and so on, and pass the result through the softmax function to normalize the values. The result is the WS matrix, which has a shape of 512 times 512, which contains information about how each of these 512 tokens attends to all other tokens. Then we multiply the WS matrix by the WTV matrix to rebuild each token's value from the values of other tokens. During this process, each token takes a portion of other token values, and the size of each portion is determined by the corresponding entry in the WS for that token pair. This step is where attention actually happens. Each token reconstructs itself by mixing information from other tokens, weighted by WS. Next, we mix in another learnable matrix, WO. We also add WT token vectors to ensure that token's attention to itself is preserved, Because tokens rarely attend strongly to themselves, we risk losing the tokens vector completely at this stage. To mitigate this risk, we add the WTA matrix. Then we mix in two other learnable matrices, WFFN1 and WFFN2. After applying the first matrix, we perform a real LU operation, which effectively removes negative values by converting all negative numbers to zeros. Then we add W power matrix to the result to obtain the WFO matrix, also known as the final output of the transformer block or the last hidden state. The last hidden state is the final set of contextual token representations produced by a transformer after all layers of attention and transformation. During inference, models like BERT output this matrix directly, where each token is enriched with information from its full context. It is important because it is the model's most complete internal representation of the input. And it can be used for downstream tasks such as classification, similarity search, or as input to task-specific layers, as well as domain adaptive pre-training. One common approach is transfer learning, where we take a pre-trained model and keep the transformer backbone up to the last hidden state. We then remove the original prediction head and attach new task-specific layers designed for our own application. Because the last hidden state already contains rich contextual knowledge learned from massive amounts of text, the model can quickly adapt to tasks such as sentiment classification, semantic search, spam detection, or named entity recognition without needing to learn language from scratch again. Another common approach is domain adaptive pre-training. It extends this idea one step further. Instead of immediately attaching a new task-specific head, we first continue pre-training the model on text from a specialized domain, such as medical papers, legal contracts, financial reports, or cybersecurity logs. This allows the last hidden state to become more aware of the vocabulary, patterns, and context specific to that domain. Once the model has adapted to the domain itself, we can then add task-specific layers on top, resulting in significantly better performance on downstream tasks within that field. Next, we mix in two more learnable matrices, W out and B out, which produces our largest matrix. We then apply the softmax function to the result to obtain probabilities. This produces our next matrix, called W largest SM, which has a shape of 512 times over 10,000. Next, we create a new matrix from scratch, this time called W1 hat, which has a shape of 512 times 10,000. This matrix contains one row for each of our 512 tokens and one column for each token in the 10,000 word vocabulary. If a vocabulary token appears immediately after a given token, the corresponding cell is set to 1, otherwise it's set to 0. Then we subtract the W largest SM matrix from the W1 hat matrix. The subtraction produces an error matrix which shows how far the model's predictions are from the correct answers. These error values are then used to adjust the learnable weights during backpropagation. Next, we'll multiply each value in the resulting matrix by itself. This produces the WSQ matrix. Then we compute the W single token loss matrix, which has a shape of 512 times 1 by summing up all the column values of the WSQ matrix. Finally, we obtain our loss value, which is simply the average of the 512 values in the W single token loss matrix. Loss is a single scalar value, and our ultimate goal is to make it as close to 0 as possible. So, we are tweaking values in the 8 learnable matrices and applying them to the WTE matrix, until the applying yields the next word, after each word in the WTE more or less correctly. Applying mostly means multiplication, with some cases of addition and other simple linear algebra operations like max, power of, etc. Next, I'll explain how to multiply matrices. To visualize matrix multiplication, imagine lifting a row from the first matrix and rotating it 90 degrees so it lines up with the columns from the second matrix. Once aligned, we multiply the matching elements together and sum up the results. The sum is called the dot product. We repeat this process for every row in the first matrix and every column in the second matrix. The resulting matrix will have the same number of rows as the first matrix and the same number of columns as the second matrix.